doing today? Good. How's it going with the assignment? How many of you have started doing the assignment? Good. The server is working okay? For those of you who tried it? Good. One thing to note, some of you have noticed this on the first assignment, but you know when you submit an assignment, you submit it to the test server. You get some stuff that shows up on the web page comes up that shows you what the results were of grading your assignment. But you also get an email sent to your Carleton email account with even more detailed information. So in particular, if you have a crash, meaning that some exception gets thrown and is uncaught, then the full details of that exception and error message show up, which point directly to the line of code where that exception occurred. So this is useful for debugging. No, that's not a new feature. That's been there for the first and second. Okay. So today I want to talk about a subject which is widely ignored in data structures courses, even though it's probably the most practically important, practically relevant data structure that we'll see in this course. It's the thing that is used the most often. In fact, there are whole programming languages built around this data structure, where the only thing in the language is this data structure. And so this data structure goes under a variety of different names, but the usual one you'll see it under is hash table. In Java, in the Java collections framework in particular, there's a couple of these things. The hash set and the hash map. Both of those are implemented as hash tables. Most of you studied Python last year. Python's set and dictionary classes, those were implemented using hash tables. And in fact, if you look a little bit under the hood at Python, actually every object in Python is one of these dictionaries which is implemented as a hash table. So every time you access an object's properties in Python, you say my object.x. Well, what's really happening is the string x is being looked up in a hash table. Another language that's completely built around hash tables is JavaScript. Everything you make in that language is a hash table. Every object has a hash table in it, and you can see this in JavaScript. If you say my object.x, that's actually interchangeable with code that looks like this. My object at string x. Here you sort of see you're doing a lookup of the string x in the hash table, but this is just another way of writing it. So these things show up everywhere. So that means that every bit of JavaScript that is ever running on every browser, on every page that goes to any page that has JavaScript code, hash table lookups are happening constantly every time an element of an object is being accessed. So these things are important. Their performance is important. They're critical. Internally, in all kinds of things like devices that run the internet, so backbone routers, even the routers on your desktop, or in the ones that are attached to your cable modem or your DSL connection. All kinds of decisions are made inside of those things about what should happen to a packet, whether it should be forwarded, whether it should not be forwarded. In the case of backbone routers, which link it should be forwarded on. Many of those things are happening based on lookups in hash tables. So lookup of an IP address or part of an IP address in a hash table. And those things happen, you know, at the big rates. They're happening in thousands of gigabits or gigabytes per second even. So tons of these things happening. This is the most important data structure. And what I'd like you to take out of this course is we have hash tables. This is the thing I still want you to remember 5, 10, 15 years from now. And we have things like different implementations of sorted sets. So that includes things like skip lists and different kinds of binary search trees. And these things solve two different problems. What hash tables let you do are exact searches. What these things let you do are what are sometimes called locates or predecessor or successor searches. So these exact searches, you know, if I say find X, you either return X or you return something like X was not found. These guys over here, if you ask me to find X, you can either return X or return something like the minimum Y such that Y is bigger than or equal to X. So the smallest value bigger than or equal to X, or so that's called the successor. So that's the value that comes after X, if X is not there, or maybe the max Y such that Y is less than or equal to X, and that's what's called a predecessor of X. Okay? So the primary difference between these things is they offer different kinds of functionality. One of them just says, here's X in the data structure, or it's not there. That's all I can tell you. This one says, here's X in the data structure, or if it's not there, here's something that's close to X. So the closest thing to X, whatever closest means. And you pay something for that extra functionality over here. These guys, at least the ones that we are going to study, they all take log n time to answer these queries. These hash tables, which is why they're used so much, they don't. They take constant time to answer their queries. And again, this is really, really important. It seems like, you know, log n is pretty small. We decided that even if n is 4 billion, log n is only 32. But still, it's substantially different from constant. Right? One of them grows as n gets bigger, so this data structure gets slower and slower the more stuff you add to it. The other one still takes the same amount of time, whether it contains 10 elements, 1,000 elements, or a billion elements, or 100 billion, or all the data in the universe. Still takes the same amount of time to determine if X is there or not. And that's why these things, well, in addition to that, the constant inside there is usually quite small. So it's something like, the typical thing we'll see is maybe it's looking at 3 or 4 locations inside an array, or maybe it's looking at 2 items inside a linked list to find X or determine that it's not there. Okay, so this is the take-home message from all of this. Remember this in 10 years, that if you don't care what happens when you search for something that's not in the structure. All you want to know is that it's not there. Then the hash table is what you want. And figure out whatever language you're using, whatever libraries you're using, figure out which things are actually implemented as hash tables. And if you do care, if you want things in sorted order, or you want to be able to answer questions like, what's the thing that's close to X, then you want a sorted set here. Don't waste your time with the sorted set if it's unnecessary. And the reason I'm making such a big deal about this is this is something that people in industry still make this mistake. They don't make this distinction even after when they should be experts in the area. For example, I have seen implementations of binary search trees, really fancy binary search trees that are not really easy to implement and non-trivial to really understand and implement them correctly. And the find operation that they implemented with them goes through the tree and searches for this thing, and then it either finds it and returns X, or doesn't find it and then it just returns not found. And that's the only interface for find in those things. Meaning that it's completely pointless to use a binary search tree for that when they could have used a hash table, which would have been faster and a lot easier to do. So keep that in mind. This is still something that people in the industry don't really understand. All right. So we're going to look at hash tables and hashing as a two-step operation. And it works like this. So we're going to imagine for now that a hash table stores a set of integers. And we'll say they're in a range, or they're a subset of 0, 1, 2, 3, all the way up to 2 to some power W minus 1. And think here, for example, W could be 32, or maybe more modern times, tell you the computer that they're running on. You'll see that once you can do this, then there's a second step where you can get hash tables to store just about anything, but that requires an additional step. Okay? So that's the goal, is we want to be able to store a set of integers in this range, and we want to be able to insert elements, remove elements, and find an element if it's in the hash table, which really in this case means return true or false. True, we found it, or false, we didn't find it. But also, you could also imagine that along with this integer that you store, there's some extra data, so that you would return then that extra data that's associated with the integer. So that's, for example, what maps do in Java. Think of there's an integer key plus some extra data value associated with that. All right. It's clear what we want to do? Good. So here's how these things work. Here's one variant of these things. And this is called, so there's a lot of different kinds of implementations of hash table. One of the oldest is called hashing with chaining. And what happens there is you create an array, call it T, and the length of this array is M. And usually we'll maintain for most of these things that M is approximately the same as N, which translates into something like maybe, for example, maybe M is, let's say, bigger than or equal to N, but not bigger than 2 times N, for example. So that's what it means for M to be approximately equal to N. They differ by a constant factor, at least when N is not 0. Okay. So we want to put data into this array, and the way we store it is in lists. So each array here, or each element of this array, stores a list. These are the so-called chains. And now all of this relies on a magic function. So there's a magic function h of x, which takes elements from this universe here, 0 up to 2 to the w minus 1, and it maps them down into the range 0 to m minus 1. So if I take one of these integers in this range, x, and then I compute h of x, well, that turns that integer, and this range is pretty big, right? This is like 4 billion or whatever 2 to the 64 is, so some huge range. And maps it down onto an index into this table. So we compute h of x, and we get an integer between 0 and m minus 1, which happens to work perfectly because this table, this array, has exactly those indices. So h of x points to, we can treat it as the index of something in this table. And in this table is a chain, and if x is in the table, it's going to be stored in this chain. There's nowhere else that we're allowed to store it. Okay? So now all the operations become fairly easy. So if you want to do something like add x to the table, it's just something like you take t, add h of x, and you append x. There's how you add something to this hash table. If you don't care about adding duplicates or any of that sort of checking there, you compute h of x, go to that location in T, that's a list, and then you just append x to that list. If you want to remove x, you just take T and h of x, which is a list, and you ask it to remove the value x, which means that you walk through that list looking for x, and if you find it, you delete it. Yep? Yeah. So h of s gets us down gets us to one place in this table, and then we have a list that we have to search through. Okay? And then finally, find x is, I don't know, you just say t at h of x, find the value x, or find finding the value of x just goes through this list, looking for a node that contains the value of x, and if it finds it, it returns. If it gets to the end and doesn't find it, then it returns false or element not found or whatever you want to do. Okay. I mean, I said skip lists were simple, but this is deadly simple. I mean, this is incredibly simple. But all of this, of course, relies on this magic function, h of x, that has to do some nice stuff for us. So, but before we get into the details of what these magic functions should do or how we even get these magic functions, I'll just point out this is a little bit of an oversimplification, just in the sense that, remember, we want to keep the table size close to the same as, so the table size is m, we want to keep that close to n. So we would play our usual tricks here of when we add something, we would make some check, you know, if n plus 1 is bigger than m, then we do, like we've done many times before, we resize the table. So we would probably double the size of the table in that case, maybe, or make it, you know, multiply it by 3/2 or something, and then put everything else, re-put everything back in the table, which we also have to look at, be a little bit careful of. That means we need a new hash function, one that takes us onto the bigger table. So not one that just has indices between 0 and m, but one that now has indices into the new table. Similarly, after you remove something, you might want to say, you know, if n minus 1 is smaller than m over 2, maybe you do some resizing then as well, shrink the table. Finally, you don't have to worry about that. And this growing the table and shrinking the table when necessary, we've analyzed that before. It's the same thing that happens in many of our array-based data structures, in particular in the array stat/array list. And we saw that that doesn't add much to the cost of a sequence of operations. So if we do m operations starting with an empty, maybe m is not a good thing to say. We do k operations starting with an empty list, then the total time we spend resizing is only proportional to k. So an average of a constant per operation. Okay. So if we want all of this to work, we want this to be efficient, then what do we need to have happen with this table and these lists in this table? So ultimately, all hashing does, or hashing with chaining, is it takes a problem of searching in a big set, the set of all n elements, and turns it into a problem of searching in a list. So what property do we need for this to work out well? Yeah? Yeah, so we don't want this list to be huge, right? I mean, we know that searching for an element in a list is not efficient. We have to walk through the whole list, you know, most of the time, or at least half the list most of the time. So we know that that's not efficient. So the only way that this could possibly be fast and efficient is if these lists are small. In particular, we want them to be of constant size, which means that since the number of lists and the number of elements is about the same, we need to spread our elements out pretty evenly over these lists. If we don't, you know, if we have one list with a whole bunch of elements in it, then then that's going to be slow to search there. And even worse than that, not only will it be that particular list be slow to search, but because that list contains a lot of elements, it somehow seems even more likely that that's where we'll be searching, because the elements, most of the elements we're looking for are in the big list. So we have to be careful. We want the elements to be spread out. And we have to think a little bit about what that means. So one thing you might say is, you might say, okay, I would like the average length of these lists to be small. Would that be enough? average? I mean, what does the average mean? Yeah. Yeah. So you want most of the list to be about the same size. So does that mean you want the average to be small? Sounds reasonable, right? Well, that's, yeah.
If we have a lot of numbers, the average itself would be the how does it make difference between one or the other?
Okay, exactly. So average sounds good. Oh, let's make the average list size small, but actually that's completely meaningless because without even looking at the list, I can tell you what the average size of the list is. It's n divided by m. Right? The average doesn't tell you anything about how things are distributed. So it's the same thing is true if I have one list here and all n elements are in it. Well, what's the average number of elements in a list? Well, to take the average, you take the sum. So that's n plus 0 plus 0 plus 0 plus 0 plus 0 plus 0 for all these lists, which are empty. And then you divide by the number of them. So it's n divided by m. The same thing is true if my list, my hash table is somehow perfect, where everything contains exactly the same number of elements. All these are exactly the same. In that case, maybe the average is, let's say that it's 2 elements per list, then it's 2 plus 2 plus 2 plus 2 2, which is the number of elements stored in the table, divided by m, which is still n over m. So the average number of elements in a list doesn't tell us anything. We can know that without even knowing what's in it. But we need some kind of better property. So we somehow want the elements to be nicely distributed or something. And it actually took a while for this to be nailed down in a way that was, for a good definition of what this was, that got at the idea that we wanted the lists to be usually short, and that we could find these magic functions which actually have the property that we wanted. And so here's the property that we want from these magic functions. So first of all, I'm going to be a little bit informal here. So h will be, let's say, a random function chosen from some set h1, h2, h3, h4. I don't know how big this set is. It's huge. Something of possible functions. So each of these is just what we think of as a normal function that maps from this range 0 to the w minus 1 onto this range 0 to m minus 1. So we have a whole bunch of possible hash functions that we could use, and out of all of those, we pick one at random. So h now is really a random choice from this set. And here's the property that we want. We want that now, if x is not equal to y, then probability that the hash value of x is equal to the hash value of y, that should be less than or equal to, I'll say, some constant divided by m, and that's for some constant c. that says, take two elements, x and y, that are different. So maybe 1 and 42. I pick a random function from this family, and I look at, well, for some of those functions, maybe h of x and h of y are the same. And for some of those functions, h of x and h of y are different. And what I want is that the probability, if I pick at random from here, that I get h of x and h of y the same, that should be small. It should be about 1 over m. So the intuitive way to think about that is h is sort of like a thing that takes x and throws it into a random spot here. It just picks one of these things at random to throw it. And then it comes along and takes y, and it throws it into a random spot here. Now, if h really worked that way, if it just threw things at random into these slots, then, well, h of x goes somewhere into one out of these m slots. And then h of y comes along later and takes a random slot. And out of the m choices, there's only one of them that contains x. And so there should only be a chance of 1 over m of picking the same slot as x. Now, of course, it's not really a random function because it's a function that has to remember where x went and where y went. So if you ask it for h of y again, it gives you the same value than x went. And the same thing for h of x. But that's the intuition, that this function really takes one of these guys and throws it into a random slot, and another guy comes along and throws that one into a random slot. And if it were really random like that, then the probability that they would both go into the same slot is only 1 over m. Like you take two random people, what's the probability that they have the same birthday? It should be about 1 over 365, right? Okay. So that's what we would like. That's the really critical property of this function that we would like is that this is the probability that two elements that are different end up in the same slot is actually about the same as what would happen if they were both thrown into random slots. Okay? Is that clear? And of course, if x equals y, then h of x is better equal h of y. But that's just what it needs to be a function. And if it has this property, then it's called a universal family of hash functions. And the family here is this thing. This set is the thing that's the universal family. And so these universal families of hash functions are good. And so now let's see what happens if we have one of these universal families of hash functions. So let's say, let's set it up. Suppose we store some subset S of these integers. There's n of them in a hash table. Using a universal, using a random hash function h chosen from a universal family of hash functions. Okay, so that's the setup. Now, What we would like to know then is, well, for some element, how big is the list that contains that element? So pick some element X and say, how big is this list that contains X? Because that determines how long it takes to search for X, as well as how long it takes to remove X. Adding X, actually, that doesn't matter because we're just appending to the end of the list, which only takes constant time. But certainly for searching and for removing, the length of the list matters. So our question is, how long is the list that contains X? Now that depends on X, and it depends on the hash function that we chose. So the real question is, a bit more precisely, what is the expected length of the list that contains? That's the real question, because there's a randomization in here. The randomization is the choice of this random hash function. So we can't tell you exactly how long the list is for a particular X, because it depends on which hash function we chose. But we can ask that question on average, when we average over all the possible choices of the hash function, how long is the list that contains X? Or even the list that we would search in when we search for X, because the list may not actually even contain X, just the place we would look for X. All right. So what is your guess, first of all? How long would you guess that this list is? So n over m. That's a good guess. So the guess is n over m, because that's the average length of a list, and hopefully these universal things, they behave like the average. But we should be a little bit careful here, because these universal things, there's still this constant c here. If this were 1 over m, then this would say this behaves just like a random function where two guys are less likely to be, they're two guys have probability exactly 1 over m of getting the same slot, but there's a c here, and so that c is going to creep up into here. So some constant times n over m. And remember, we've been keeping n and m about the same, which means that it's going to be O c, but if c is a constant, that's going to be all 1, so constant. So as long as we keep n and m the same, and something like this is true, this is the expected length of the list that contains X, then we're golden. And now we want to somehow prove this rigorously. It's not hard, but there's a couple of cases. So first thing is, case 1, if X is not one of the elements that we're storing. Okay. So we've got this hash table. And the hash function tells us that if we want to look for X, we should look in this list. Now, and we're curious now, so X is not going to be in that list, but there's going to be some other stuff in general in that list. any of the other elements, any of the elements in S. And we'd like to know how many of those. So let's start listing the elements in S one at a time. Let's give them names. Let's call them, so the elements that are in the table, let's call them y1, y2, y3, y4, y5, up to yn. So, look at y1. What is the probability that y1 is in this list? Which is the same thing as asking, what's the probability that h of y1 is equal to h of x? What can you tell me about that? Yeah? Yeah, it's at most C over M, because x is not in the list, so in particular, or x is not in the set, so in particular x is not equal to y1, so we satisfy this condition, which means that this condition holds. And so the probability that this, if that's true, is less than or equal to C over M. Y7 and so on. And so each of those things, each of those n elements has a probability C over M of being in the same list as x. Okay. So I mean, we can do this the long way, but that means of the n elements, each of them has probability C over M of being in the same list as x, which is means that the expected length of that list, the expected number of those elements which actually are on the same list as x, is Cn over M. Expected length of the list T at h of x is equal to. Okay. And if we want to do that in a long, very long-winded way, we can do that by saying we'll define an indicator variable which is I, which is equal to 0 or 1, and it's equal to 1 exactly if h of I, h of x is equal to h of I and 0 of x. And then the length of that list is the sum I equals 1 through n of I. And the expected length of the list is the expected value of that sum, which is the sum of the expected values. And then finally, these expected values are easy to compute because we know exactly the probability that this thing is equal to 1. It's less than or equal to Cn over M. So it's less than or equal to C over M. Which is finally equal to Cn. So this is just a slightly longer, more formal way of saying we have n items. Each of them has probability C over M of being in the same list as X, or the list that X chose. And so, so in the end, the expected number of those is Cn over M. That's a fairly typical kind of situation where you have a bunch of items, and in this case, each one has the same probability of having some property. In this case, the property is being in the same list as X. And so once you know the probability and you know the number of those items, then you know the expected number of items that have that property. You just multiply those two things. Okay. So question there? And in our case now, that means that we have been keeping n, well, whatever you want, n between, well, in our case, n over m is less than 1, less than or equal to 1. So this is actually right, because if m equals n, which is the lower end of the range, then this is 1. Otherwise, if m goes up to 2n, then this is a half. So in any case, we're less than or equal to c. Okay? And case 2 is just the case where x actually is in the set x. And all that means is, well, we have the set S, which is y1, y2, y3. Somewhere in here is yi up to yn. And it just so happens that yi is equal to x. So what can you tell me then about, so the thing to look out for here is, in this case, when x is not in the set, it's possible, if c is, I mean, it's possible to get the expected length of the list is smaller than 1, the list that contains, the list where x would go. But if x is in the set, well, we know something about the length of the list. It contains at least x, so its length is at least 1. So we just have to twiddle that a bit. But that's also easy. All we do now is say the same thing. We have n minus 1 elements. These are y1 up to yi minus 1, yi plus 1 up to yn. That might be in the same list as x. And we also have x in that list. And then you just do the same thing. So the expected number of elements x, that is less than or equal to n minus 1, each of those elements, times c over m. And then we shouldn't also forget that x itself is in that list, so we get a plus 1. And with our assumptions, n minus 1 over m is smaller than 1, so this is less than or equal to c plus 1. So of course, if you know x is in the list, then you know the length of the list is at least 1, and then there's all these other elements that may or may not be in the list as well. And the expected number of those is at most c. Yep. I'm writing n minus 1 because one of the n elements is x itself, which is definitely in the list. So that's where the plus 1 comes from. And then each of these other n minus 1 elements has probability c over m of being also in the list. Plus 1 for x. This is. Okay? So the whole thing that makes this work is that if you just take any two elements that are different, and then the probability that they end up in the same location is only about what you would expect if you just threw them into random buckets. But there's a c here instead of a multiplier. It took surprisingly long for that to really become formalized and realize this is sort of the weakest property that you can have that makes this work. And once you know what the property is that you need, sort of the minimum such property, and that's this thing, then you can start looking for these these sets of hash functions which are universal. So I'll show you one of those. We won't prove that it's universal, not because the proof is particularly hard or long, but it requires both probability and number theory, which most of us here don't have, well, have little or no experience in, let's say. So the proof is in the book if you want to read it, but it's not critical. So all we need now is one of these universal families of hash functions. This actually is another thing that took surprisingly long to come up with. It wasn't until 1996 that this was found. So this is about 46 years or so after the first hash tables were used in computing, and nearly 20 years after this property was defined, this minimal property. So it's not the first one that has this property, but right now it's probably the most efficient one and the one that should always be used in practice. Until somebody comes up with something better, but we don't know of any better ones yet. And so I'll write this as HA of X, well, first one condition. So we already said that these things go W-bit integers onto 0 m minus 1, but I'm going to require that m is equal to a power of 2, so 2 to the d. So then these things are really W-bit integers down to D-bit integers. So to use these hash functions, you have to have a table size which is the power of 2. And then the hash function looks like this. So the hash function is parameterized by some value of a. And you take a, and you multiply it by x, and you take that mod 2 to the w, and then you do an integer division by 2 to the w minus b. So that's the hash function, HA of x. Now, I promised you not just one hash function, but a whole family of hash functions that I get to choose from at random. So what's the family that you get? Where are all these different hash functions? Well, you get different hash functions by choosing different values of a. So a could be 1, or a could be 3, or a could be 17, or 43, whatever. So you choose different values of a here, and a is chosen to be a random, odd, W-bit integer. Okay. All right. So that's the family of hash functions. So that says our family of hash functions is h1 of x, h3 of x, h5 of x, up to h2 to the w minus 1 of x. So there's 2 to the w divided by 2 of these possible hash functions we can choose. Take any odd integer in this range, and that gives you a different hash function. Okay. And the theorem of these guys is that they are universal, and that is if x is not equal to y, and a is a random integer in 0 up to the -1, then the probability that each of x equals each of y is only 2 divided by x. So 2 is a constant, so it's 2 divided by x. That's the C from the definition of universal. Look a little more closely at this thing. Why is this such a good hash function to use? Well, it's good because it's really fast to implement. So let's draw what's happening when we implement this hash function, when we execute this hash function. So we have A. We have A, which is a random W-bit integer that's odd. Odd just means that the last digit is a 1. Everything else is just random. So in fact, just pick a random W-bit integer and then OR it with 1 and then get another one. Then we have X, which is I don't know what, and then hence whatever. It's probably not random. So this would be X is 5 in this case. So what does the hash function say we should do first? Definition. It says we should multiply A times X. Remember, these are W bits. So in general, if we multiply two W-bit integers, how big of a result do we get? W. So you need twice the number of bits to hold the result of this multiplication. In this case, it won't be so much because there's so many zeros here. So let's make it a little more interesting. We'll put a 1 there. You multiply these two numbers, and you get a huge number. So if W was 32, you get something that in general has 64 bits. So this is not really these two numbers multiplied. I'm making this up because I don't feel like multiplying these two numbers right now. So you get this huge thing, and now this is 2 times W bits. Now what's the next thing that we do in this hash function? We take this whole thing mod 2 to the W. In this binary representation, when you take something mod the power of 2, what does that mean? You do an AND, but then you can do it with an AND. But what is if this is the number that I'm taking mod 2 to the W, is it easy to know what that is? Just how do you do that? Yeah? Yeah. When you take this mod, so this is A times X. And now if I take this mod 2 to the W, all I do is scratch off these bits here. And keep only these ones. These W bits on this side. But wait a minute. W was 62 or 34. And that depends on, let's say, whether your computer is a 62 or a 34-bit computer. So if I have a, let's say, a 32-bit computer, and I take two 32-bit integers, and I multiply them, what comes out? You only get a 32-bit number out of that. So the true answer is a 64-bit number. So what 32 bits do you get? You get the lower 32 bits, you get these ones. Okay. So in computer code, a times x mod 2 to the w, if w is the number of integers in your, the number of bits in your integer, that's the code for that, just a times x. The overflow happens and all these other bits get thrown away anyway. So the mod 2 to the w is a free operation. It's an artifact of the way fixed precision computers do multiplication. All right. Now the last thing we have to do is do an integer division by 2 to the minus w. So when we take a binary number and we divide it by a power of 2, what are we really doing? We are wiping out what? We're getting rid of what? We're dropping the least significant bits. And the number of significant bits that we're dropping is whatever the exponent is in the power of 2, so it's w minus d here. So what we're doing when we take this ax on 2 to the w divided by 2 to the w minus d is we're killing off w minus d bits here. This integer, so we would be right shifting, and all of these bits would become fractional bits. So this would be a half, a quarter, an eighth, a 16th, and so on. But we're only keeping the integer part, so we're really just keeping this thing here, which is d bits. And on a computer, this is a super fast operation. It's the right shift operation. So you just take this number and you right shift it by w minus d positions, and you're just left with these d bits here. And so that whole thing in Java looks like this. So that's that's h of a of x. If we were to write it in Java, and that would be for an int a, an int x, and that would be when w equals 32. So it's pretty tough to get a hash function that's going to execute faster than that. Really, one multiplication, that's the hardest part of the thing, and then the right shift is trivial. That's the fastest operation you can do on a computer system. One of the fastest operations. Okay. So it's a super easy function to implement, and it has this great property of being universal. Okay. So now we have all the pieces. We know how to make a hash table with chaining. If we have a universal hash function, we know how to prove that hashing with chaining has a constant time to add, remove, or search if we have a universal hash function. And now we know how to make a universal hash function or universal family of these things. And picking from that family is super easy. All you need to do is pick this random integer a, and then make sure that its least significant bit is 1, so that it's odd. and then that all works. And so the end result is that if you do the theorem here is that chain hash table that uses multiplicative hashing as constant expected time for add, remove, and apply. And in fact, we can look really carefully. If we do this, I mean, it depends. We said that there were some bounds on M, like maybe, in this case, probably you would want M between, the good one is between, so it's bigger than the number of elements you're storing, but it's less than 4 times the number of elements you're storing. And now we've gone through this proof. So in particular, this is the important thing, that it's bigger than the number of elements you're storing. So the C in this universal thing is 2, and so we figured out that when searching for X, we get a list of expected length less than or equal to 2 or 3, depending on whether X is in the table or not. So if we search for something in the table, then the expected length of the list we're searching for is less than or equal to 3. It's 2 other elements plus the one we're searching for. If it's not there, then there'll be 2 other elements on it. So this is really fast. This basically says you take any set, 1 billion elements, you make this multiplicative hash table, and now this is what you use as your hash function. So to look for X, you hash it this way, super fast. Go to that place in the hash table, and what you expect to see there is a list with only 2 or 3 items in it. So the problem of searching in a set of size 1 million or 1 billion or 1 trillion reduces to searching in a list of size 3. Very powerful stuff. All right. So what's left is, well, all of this relies on you only storing integers in the table. And we know that, well, all of these things we've used, things like dictionaries in Python, or sets in Python, or hash sets, or hash maps in Java, you can put any objects in those things. So the question then is, how does that happen? Well, the whole procedure looks like this. In general, what you start with is some object, and that object is usually not an integer. Or maybe it is even an integer, but it's an integer that's not W bits. Maybe it's 2 times W bits, or maybe it's a variable number of bits. And I need to get that thing down into an element of this set. Once I do that, then I can hand it off to the hash table, which will take it down again and put it into an array location using whatever it sets internally. So the hash table handles this part of the picture. And then there's this getting from an object to an integer here. So do any of you know in Java what that's called? Called what? Yeah, it's from here to here, this is done by calling the object's hash code. So every object, in fact, the object class implements a hash code method. So for an object, you take its hash code method. What comes out of that is an integer, an int in Java. And that's one of these 32-bit integers, which then the hash table uses to do this stuff. So in particular, it's the hash table which we'll call the hash code method to decide what it does. Now, so we've already seen that the hash table can screw up in the sense that if it takes a bad hash function here, it could easily make all the elements go into one list. That would be bad. But there's plenty of room to screw up here too. And in fact, this happens all the time. If you look through the Java code, we'll look at some examples. It's full of bad implementations of hash code. Really, really, really bad. Where it's easy to make all the objects have exactly the same hash code. In fact, you can make them all have hash code 0. If that happens, then there's nothing the hash table can do to help you. Basically, the hash table, it stores integers, and it can help you if you keep adding the same integer over and over and asking it to store the same integer. It's just going to put them all in the same big list somewhere. It has no other way to do that. So that's what happens here. And now it's worth, I'll do this again, but I'd like to point it out now. So every object has a hash code method. It's implemented in an object. And do you know how this is implemented for the object class if you don't override it in some object? You know what this does? Yeah? Yeah. So the default implementation is, this is basically just the memory location of the object. Now every object also implements the equals method that compares it to another object and determines if they're equal. And do you know how it implements that? So it checks if they're identical, which means that it actually checks if the two memory locations are the same. That's what it means to be identical. It means these two objects, which are references to the same memory location. So this basically compares, let's say, A dot equals O compares A's memory location to O's memory location. Now, sometimes we want a more useful definition of equals for objects. Like we might have an object which is a person, and we might say that two persons are equal if their first name is the same and their last name is the same. So sometimes we override equals to mean something other than these things refer to the same object. So you might say, A's first name is equal to O's first name, and A's last name is equal to O's last name. So that might be how you redefine this thing. Now, if I put a bunch of people into a set, for instance, now we know what's happening. So each person gets, the set basically takes each person that you put in, takes its hash code, and then uses that to determine where it goes in the hash table. So let's think about this. So I'll say A is equal to new person Warren, and B is equal to new person Warren, and S is equal to new set persons, and S dot add A, S dot add B. So what should happen here is if I use this Java code. So, yep. Well, so A and B are two persons with exactly the same name. And that means, and if we redefine what it means to be equal, then to having the same name, then that means A equals B. And so the set should not have B, because you're never supposed to have two elements in a set that are equal. It should not have B. But if we look at the picture of this thing in memory, what we've got is A is a reference to some memory location over here that has all the data about this person. B is a reference to a different memory location, which has all the data about this person. And in particular, A's hash code, which is really just this memory location, it's not equal to B's hash code. So the set takes A, computes A's hash code, and then takes hashes A's hash code and says, okay, A should go here in this list. And then along comes B, the set hashes B's hash code. Usually these two things end up being different because they get different inputs. This is X, this is Y, and X is not equal to Y, so most of the time you get a different place here. So then the table goes and says, okay, that guy goes over here in this list. Well, we're adding them, we'll make sure we're not adding a duplicate by looking at the elements in this list. Okay, good. None of them is equal to this, so we add it to the end. So now we have both B and A stored in this hash table, and that should never have happened. So that's where this golden rule comes from, which is the golden rule is never redefine equals without also redefining hash code. If you do, then sets, if you redefine equals without redefining hash code, then everything stops working. All these data structures won't work the way they're intended to. The next class we'll see how you define good hash code for your objects.
Or Sheen. What? What? Sheen. Oh. Once I give up, I'll just go to the Remember the slide you were on? It said fetch, and then that's when you increment PC.